Welcome back, everybody. You are indeed at the second lecture of Scientific Computing for Physicists. And I don't know if I mentioned that, but if you're not a physicist, you're still very welcome. It is really for sort of physical science applications. So let's go on with the lecture. Just a few things to note. We had a very productive hands-on or office hours yesterday, where I demonstrated some ways to get into the teacher cluster. If you couldn't attend, we're going to post the recordings on the website, and it might be useful for you to look at if you have any issues. Furthermore, you should pretty much all have an account to get into the teacher cluster now. So you're going to need that because at the end of this day, and not right at the end of the lecture, but we will post an assignment on the website that you will have to do on the teacher cluster. So if there are any questions, feel free to ask them. There'll be office hours on Friday at noon, so that is a good spot. Yeah, so if you haven't received things or there's any other issues, just email us and we'll straighten it out. Now, because we want you to do the assignments, today is going to be an overview of C++ techniques that we will be using in the lecture, in the lectures. As I explained, it's the C++ Lite, really. So if you are more versatile in C++ than what we will present today, that's fine. You can use that as long as it's C++14 compatible. That's sort of the standard we're using. Okay, so we went through all of this on Tuesday. So let's go to the C++ part then. Okay, so we're going to use these particular elements of C++. That is to say, that is all we really expect of you, and more are allowed. And so if you're coming from a different language than C++, a lot of these will still sound familiar. They'll just work slightly differently in C++. If you've not worked with a compiled language, that's going to be your biggest change apart from the syntax. So we'll go over these, and it'll be, if you know C++, it's going to be a slightly boring lecture, and I apologize, but at least you kind of know what our baseline is. So we're going to look at variables, we're going to look at functions, we're going to look at loops, we're going to look at pointers, which we will use a little bit, dynamically allocated arrays, conditionals, objects, templates. The objects and templates are really things that are very C++, but that we won't be writing much of, but we'll be using them. So we'll cover those. Libraries that come with C++, and a few other things. So variables, and this is sort of excuse me. This is an implementation of the concepts that I talked about last lecture. So they're basically named pieces of data, right? So we need to be able to create variables and manipulate them. Now in C++, which sets us apart from some other languages, every variable has a particular type. So a variable has a name, and that name has a particular type and can't change its type. Like it's that particular type. So it's what's called a strongly typed language. The data that's stored in the variable can change. That's why it's called a variable. It's not just a constant. So we can't reuse the same name for the same. You can do that in Python. You can have a variable that is an integer at one time, and the next line it becomes a string. Not so in C or C++. So what does a variable definition look like? You have to first say what the type of the name is, what the type of the variable is, and then give its name. And then potentially, or sorry, optionally, you can give an initial value or leave it uninitialized. So there are several basic types in C++. You can have floating point types, so those are numbers with a decimal point of different precisions. So float or double, which is double precision, or long double. You can have complex floating point types as well. They're in one of the standard libraries, so they look a little bit more complex, but we'll see how that syntax works. But float doubles and long doubles are the main floating point types. You have integer types. The different types of integers really just mean how many digits can I have, but because it's binary, it's really how many binary digits. So there's short with not that many, int with more, and long with even more digits available. So those are the numerical types. Then there are character strings that you can have. You can have single characters. You can have a string of characters, and we'll see why that is a char star. And we can have something from one of the libraries, which is an actual string. And we'll look a little bit more at that. But since we're doing numerical computing mostly here, we won't use strings a lot, but eventually we will have to read in from, say, a file. A file has a name, and a name is a string. There's a character called bool, and that can be true or false. Yes, so the integers can, if it's unsigned, it means it cannot have negative values, which basically doubles the possible values of an integer. So say the short that is signed can at most be 32,000 and a bit. The unsigned version can be 65,000 and a bit. So that, yeah. But that's a sort of a technical detail here. There's other types too. You can make arrays. You can have pointers, class, structures, enums, types, unions. We'll look at arrays and pointers and classes a bit. The rest are very useful in certain contexts, but we won't dwell on them too much because they're rather specialized. So some examples of how a definition of a variable would look. Here's int. Int is a type. So this is just a. After this statement is an integer of type a. A can then be assigned a value by saying a equals 4. As you might have noticed, everything has a semicolon behind it. Every statement in C++ should end in a semicolon. Forgetting a semicolon can often lead to kind of confusing error messages from the compiler. So the nice thing about having that convention, though, is that if you have a really long expression, you can just write it over several lines in your editor, and there won't be a syntax error as long as the last line has the semicolon. Some float examples, so it works differently. Similarly, you can indicate whether a value is single precision by a little f. By default, if you don't, so 4.0, it's a double precision number. And then you can do things with these numbers. You can add them, you can subtract them. There's nice operators like plus equals, which let you augment d by f, and so that's possible. D remains a double when you do that. The types are strong and always present. If you have a string like hello there, you can put it in a char star. So you can say char star equals string equals hello there. There are some technical issues here that we'll come to later, why this is actually not so much a string as a memory location, but that's for later. And we can have true, false values, like this Boolean variable is called it is 2018, and its value is set to false. Okay. We can make all of these constants as well, so then I cannot do an assignment, and I better assign it when I have it by putting a constant in front of the type. And it kind of becomes part of the type. So there's a type that's an integer, there's a type that's a constant integer. Const is extremely useful, and if you're doing serious C++ work, you should use it all the time when something is actually constant. For the purpose of what we're looking at, we don't really mind too much if you're a little loose with what is constant, what's not, because it can be tricky to get everything const correct. So those are other types. Another very important thing to make is that if you do not initialize your variable, so you have a variable, sometimes you define it, but like here, you didn't give it a value, its value is not 0. There's not a natural initialized value for these. They have some random value. Essentially, a variable is it's stored somewhere in memory. So when int a is sort of executed or is enacted, a memory location of probably 4 bytes is given to a. Whatever was in that memory before is what it has. So there could be some random garbage that's left over from another application or another function that was called before. So make sure that you either use your variables right away, so assign it right away, or give them some initialization. It's don't assume that they are 0 initially. So there's a question. Yes, so I did this kind of on purpose, but I didn't expect a question so soon. When I'm adding a float to a double, that seems like there's something going on because they're not the same type. So although C++ is strongly typed, there are some automatic conversions that happen, but the variable type never changes. So what happens in this case, for instance, is f is converted to another variable. It's not a variable because it doesn't have a name, another value that is a double precision, which is a pretty simple conversion to do, and then add it to D. So f is unaffected, D is augmented, but it's still a double. And there's no, you can't make this variable something else. It's never dynamic. So the random value is of that type, but it really, every variable is stored as some bit sequence, right? And it really, the type says how to interpret that bit sequence. And so that's what it does. So it takes those bits that are there, or those bytes that are there, and just interprets those as whatever random value it is. So it usually makes no sense. Often for floats and doubles, you get things like infinities or ridiculously large or small values. Because the interpretation of what was there is nonsense. Now you shouldn't. I mean, you shouldn't rely on that in any case. Yeah. Okay, so those are variables. Another important part is functions. Functions are pieces of code that can be reused by invoking them by their name. So they have a name. They also have a set of arguments, which are the input to that function, and a set of, or one particular output, which is a return value. So when we specify a function, now, because they're reused, they become black boxes. And so the part of the code that is going to use this function only really needs to know what's the name of the function, what are the arguments that go into it, and what kind of stuff will it give me back. And so those 3 properties together that are enough to use the black box, but not actually implement it, are called the function's signature, or sometimes called prototype. So to write a piece of code that calls that function, use that functions, all that is required is the signature definition. So we need to declare that there is a function of this signature, but we don't have to, the code that is using it doesn't need to know how it's implemented. And that's a very powerful mechanism that it inherited from C, that allows you to make modular code, pieces of code that are in different files, that are reused, that are in libraries. We'll see how useful that distinction between a declaration and the actual code, which is often called the definition, which is a little confusing, but that's how people call it. So we have a declaration first. So here's an example. It's easier to see. So here's a bit of code. It's a C program. But I didn't say yet, it's the first thing I should have said. Any line that starts with // or ends with // those are comments. Those are ignored by the compiler, so they're very useful to put notes in. So this would be a file called funcexample.cpp. It uses some external things, but here's a function prototype. So we have a type, then a name. So that kind of looks like a variable, and then the input goes into parentheses. So the input also has to have specific types, AA, double B. This is only the prototype. I haven't said what is going to happen when I pass A and B into arithmetic mean and what it does with it at this stage, like when I go from top to bottom. But the main function here can actually call this function. So the main function, when called, would assign x to a value, y to this value, and then return the arithmetic mean. So this function also is a full function. And here, this main function, and that is common for the main function, will produce an integer and doesn't have to have any arguments. So we'll see how that plays out in a second. But this main function calls arithmetic mean, but doesn't know how it's implemented yet. That can come later. It can come earlier too, but it can come later. And in this case, that's the definition. So the definition says take the square root of a times b and return it. So we have a prototype or declaration, and we have a function definition over here. When we get to modular programming, we'll make a lot of use of this later on. Now, to use this code, we would log into the cluster. And load the compiler, and we can compile this code. So it's called func example, and we can run it. Now, it doesn't do anything. And so here's a few details that are very important initially to understand how C++ works. When I run a code, what actually happens in C++ code is that it is calling the main function. So every program has to have a function called main, and it has to return an integer. It's allowed to have some other arguments too, but it's also allowed to have no arguments. And so I have no arguments. That makes sense because I'm not passing anything. But it does execute this function. It does assign x equal to 16, y equals to 1 RSS, and it does compute the arithmetic mean, but it then returns it. Now, where does this return value of main go? And that it actually does go somewhere. It's given back to the shell. So we're here in the shell. We type the command, and it returned a value, but it doesn't print the value. We didn't say print anywhere. We just returned it. It goes into a special variable called an exit code. And it depends slightly on the shell you're using, how you get the exit code, but the bash shell that we're using on the teach cluster and in many other Linux shells, it is $question mark that encodes this. So in the shell, printing something goes with echo, so echo $question mark gives me this return value. So now the return value in main is usually used just to indicate if something went wrong. So that's good to know. You shouldn't really do it to get an answer. You should only return a value if something went wrong. By convention in the Linux world, if an application has an exit code of 0, it was successful. If it has an exit code that is not 0, something went wrong. So it's an indicator of whether something went wrong. So kind of using that here in an incorrect way. So if you want to do this in another file, there's a question, like you want to do the definition in another file. In fact, you could just cut out this part, this bottom part, put it in a different file, and add that file to the command line here. You could also do them one by one, but that's for a different lecture. But it is that simple. You just put it in another file. Each file can compile separately, but they can't make an application until you what's called link them together. And so we'll get to compiling and linking in the lecture on modularization more specifically. But basically, you just cut it out and put it in another file. So I've said this all, but in the example. But so when you declare a function, it has a return type, a name, and then arguments. When you define the function, so the implementation, which can go in a different file, it doesn't have to. You have the same form first, but then the block of code to be executed when you call the function is in between curly braces. So blocks of code in C++ are delimited by curly braces. They have to also match. This is another somewhat easy to miss or easy to make typo by forgetting a curly brace to close an opening brace. Most editors will sort of tell you where the matching is, so it's gotten a lot easier. And so there's going to be some statements, variable definitions and statements and computations, and then at the end of the function you can return something. And that return has to be of the same type as what you specified here. Okay. So that's the definition. And to call it, to use the function, there's a couple of ways to do it. I can call the function with its name and an argument list and assign it to a variable. So if I had another variable, then that would be possible. So the return value of this function goes into that variable. I can also just use that expression, name argument list, as if it is a value, because it is, or it will be when it's called, and then pass it to, say, another function, or pass it to the return statement, as we just saw. And then there's special functions that do not return anything. Maybe they're modifying things that are in argument list or something like that. So how do we do that? Because we have to have a return type. There's a special return type, and it's called void, VOID. And that really says this is a function that returns nothing. And if it returns nothing, I can just call it by its name and argument list without assigning it or using it in any sort of way. So let's look at some more examples, and examples that have things to do with how the arguments are used. So there's two ways to pass arguments to a function. So the arguments are these guys, right? The ones in the brackets. And so here's an example of one way to do it. It's called pass by value. And I have a function, void inc, and just for brevity and to make things work on the slide, I did not separately do a declaration and then a definition. I just did the definition at the top. This is also allowed, and if it's a single file, that's okay. So I have a function called inc. It takes an integer in, and it doesn't return anything, but what it does with the integer is it reassigns the integer I to I plus 1. Yeah, so if a function is void, it doesn't return anything. So it must perform some sort of action on the variables that are either passed in, or maybe it writes to a file, say, and then that file lives on the file system. So you don't take that as a return type. It's just something that happens in sort of the larger state. So I should be increased, and here's my int main. So when I run this code, it should run main. I assign 10 to the variable j. I pass j to the inc function. It will increase it, and then I return j. So let's see what happens. So I'm compiling it. G++. This works in any standard, but I specify the standard on the slides just in case. Passval.cpp is the name of the code or the source file, and the output is passval. And then I execute it. And again, I don't do this in real life, but it's just a little easier to see what's going on. The return value of main sits in this $? and is 10. But wait a minute, wasn't it supposed to increase the value? And so, yes, it was, and it did, but it didn't. What is happening here is pass by value. So what's really happening when this code is running is that in the first line of main, j is set to 10. It's an integer that has a value 10, and this is passed to the inc function, but it's passed to the inc function by copying the value into a new variable, which is called I inside of the function. So we've got I inside of the function, and that new variable has a copy of the value of j. So its value is 10, and its value gets increased to 11. But the original variable j is left behind. This is a separate independent copy. That's what pass by value does. It creates a copy of the value of the variable and puts that into a new variable, which is really the argument here. So although I is increased, we can't see it, but you'll have to trust me that this was actually done. The original j has not changed. Now that's obviously weird. Like, we don't want this. This was supposed to be a function that increases the value. Is there another way to do that? And there is. But we have to indicate that we don't want this copying to happen. And so that's possible in C++ by using what's called pass by reference. So the difference between the two is, it's hard to see, so I'll go back and forth a little bit. The only thing that was added here was an ampersand. C and C++ really like to do things with just single characters, which can make it initially seem a little cryptic, but it's not. So something to get used to. Ampersand means do not pass it by value. Consider I as a new name of the variable that you're passing. So rather than copying the value, you're copying, as it were, the memory address. But really, you're just renaming j into I. So when I do that, when I make this small change of an ampersand, j, when passed, is not copied, but is referenced. So I is now a reference to j, and when I'm increasing I, since I is referenced to j, it increases j, and when it returns 11. So this looks like using a pointer, and behind the scene, that is exactly what's happening. But as we will see when we look at pointers, pointers are memory addresses. This is a name of a variable. So I didn't have, so if it was a memory address and I add 1, I just go to the next spot in memory, which is not where my variables at all. So that's not what's happening. I is a different name, a different reference to the same. So it works using pointers. So if you've seen pointers, yes, it works with pointers behind the scene, but it is a reference, a renaming, if you want, of the same variable. I just set this, j set to 10. It's a reference. I gets increased. I is equal to j. They're the same object, just by different names. And now it's returned and it works. There's a lot of operators that you can do. I just put them here. Most of them make logical sense, that you can do with especially with numbers. You can add numbers, subtract them, multiply them, divide them. You can take the remainder. So this percent is a remainder operator. Can be very useful. You can assign. You can add to something. So plus equals adds b to a. We saw that in the example. You can subtract, minus equal. You can multiply by, star equals, and divide by, slash equals. And I think there's a percent equals as well that I haven't put in here. You can also increase by just one value. So a plus plus actually means a plus equals 1, means increase the value of a by 1. And there's a minus minus as well, which I think just fell off the slide. This is where C++ gets its name from. It's C, but then augmented. That was the idea. That's why C++ is called C++. Logic operators, you can see if two things are equal, that goes with two equal signs. That is important to distinguish from a single equal sign, which is an assignment. So if I said A equals B, B would now get the value of A. Sorry, A would get the value of B. That's not the same as asking whether A and B are equal. There's not equal, it goes with exclamation mark equals. Once you already have a truth value, you can put the exclamation mark in front of it. So if A is a Boolean, it's true, then exclamation A would be false, etc. You can ask if two things are true. So A equals and. So and is B. We saw the and was already used for references and it's used for other things too. That's why that's one of the reasons why there's an and. So and is a logical operation, or bar means or. It's also possible to write in C++ A and B and A or B, or not A for exclamation A. People tend to not do that. I am not entirely sure why. I guess they don't like the fact that there's an alternative. You can use either or. you can't use either. You can only use or. But yeah, that is also possible. And then logic is possible. You can see if things are less or equal than something, or less or bigger, etc. So there's a lot of operators. A lot of these operators sort of map quite nicely on what the CPU can do, and what you would want to do, especially numerically. Now, one of the things that I should mention, and it's a funny thing that happens in C and C++. It happened in Python 2, but not in Python 3. I'm actually not sure what R does, or Fortran for that matter. But in C++, 1 over 4 equals 0. And so the rationale for why this is the case, this is an integer division. Both 1 and 4 are integers, and therefore the result should also be an integer, is the rationale behind this. So, well, the closest thing to an integer that can be a quarter is 0. It actually always rounds down. So when I just write literal values like this and there's no dots, it is an integer. So even constants, even literal constants, have a type in C++. And if they have no periods in them, if they have no dots, then they are integers. So that's true for all of them. So if I do high between quotation marks, it makes it a string. If I have 0 without a dot, it's an integer. If I can do exponential notation with e minus 4. This is a float. It's actually a double position float. If I want it single, I have to say that it's an f. All of them have types, and the result of operations depends on the type that's going. So we have to fix this somehow, because sometimes we do want this. And so we have to convert these values, 1 or 4, to a float. If they were floats, it would work. So now one way to do that is actually to write them with a period. So 1.0 divided by 4.0 would give you 0.25. But suppose that we were already given integers and we now want to compute them. We can also convert them into a different type. So if you have a type, if A and B are set to 1 and 4, and C is our integer division, so that's going to be 0. D, if I want it not to be an integer division, should convert A and B to floats. And the old style C way of doing that, or old style C++ way of doing that, is to use the name of the type as if it's a function. And that works. And it works actually perfectly fine for these basics formats. There's a more official way to do it in C++, but this works perfectly fine for basic numerical things. And it converts A into a float and B into a float, and then does the division. And so if we run this, it actually will print out 3 values. It prints out C, D, and int, and then again the int of D. So int of D reverses this, and it essentially cuts it off. So our first result C was 0. Our float converted one is 0.25, and our integer is 0. There's a proper way to do this casting. Let me mention that first. You're supposed to say static casts and then the type, so float here and then the value. That's because there are ways to do more complex objects where a literal casting isn't going to work. But we're not really going to get into that. Now, another thing that I should mention here, because we saw it in the first example in the lecture that I didn't really explain all that well, is that we can do printing. We can write out to the terminal. And we do that with this library or this header file called IOStream. So I want to be able to print to screen. I have to include a library. And in this case, the library I include is IOStream. So the syntax goes like that. Pound include starts including what's really a bit of source code, but you can think of it as a library. And then IOStream is the name of the library. It's a standard library that comes with C++, and those you always put into these special brackets. Again, this stems way back from C, that anything that is between these angular brackets is a standard library, in contrast to, say, something that you wrote yourself, which again we'll look at another time. So this makes available to us a special object called std : cout for console out, that can write to screen by streaming things. This is the stream part here. This is a streaming operator, lesser than, and so we're streaming C into the console. What it really means is we're printing its value, so that's 0 here. Then I want to print a space. If I don't, it won't print a space. And then I want to stream in D. So, and D is 0.25 here, and again a space. And then I want to stream into the console D, which is the integer version of D. And so that is 0 again. And then if I want to end the line, so I want to go to the next line, I have to stream in this std end L. So that is what would happen if I didn't do that, is that the next prompt would happen right behind this. So that would be a little bit annoying. So this prints to screen, so to the terminal, which is nice because we are working in the terminal anyway. We'll see how you might want to write things to, say, a file or something similar, but that's how this works. Okay, so As we already saw in the d plus equals f example, there's automatic casting going on sometimes. So one of the ways you can do automatic casting is just it's a float can be upgraded to a double. We saw that. In this case of the 1/4, it's actually enough to have only one of them be a float, and then the other one gets basically converted to the type that can take the largest range of values. So this essentially 1.0/4 is equal to 1.0/4.0 because 4 gets upcasted into a float. The opposite can also be true. You can have a function, say here's a function called unchanged. It takes an integer and returns the same integer. If I pass it a float, the compiler is not going to complain, but it's going to silently change your value here to an integer. The only way it knows how to do that is truncate it. So I is actually 2 inside here. It can't be anything else. And so this isn't really returning an unchanged value. This is just returning 2. So it's something to be aware of. This typically happens when you've made a mistake. You wrote a function, you wrote int by accident, but you really meant it to be able to take a float or a double as well, and you should have done that. So it's often a bug more than anything else. But this is slightly annoying at times when it doesn't help you. On the other hand, it is very useful because it also means that if I had written a function that takes a floating value and I pass it a double, it still works. So I can, there's good parts and bad parts to this automatic casting. Okay, so those are variables and functions. Another important theme in programming is loops. So let's look at a loop. A loop is when you want to do the same thing for multiple cases. There are 2 main forms for loops in C++. There's a for loop and a while loop. The while loop is actually kind of similar. You keep doing a bunch of statements that are into curly braces as long as a certain condition is true. So the condition is probably going to depend on a variable, and the variable is changed in the statements, and that's how this loop eventually ends. Another way that is more idiomatic for C++, or at least it used to be, is that you say for, and then you give 3 statements. One initializes your variable. Second is the condition, kind of like the while, and then what should happen from one loop iteration to the next, also called the increment. An example is easier than actually just explaining that. Here's a main function. It's supposed to print out the values 1 to 10. It does that by doing a loop. And the first initialization statement here defines a variable. The variable is called I, and it's set to 1. So I'm going to have a counter here. I is going to be a counter. It's an integer counter. The next statement here, so the semicolon starts the next statement, is to check whether I is less or equal than 10. If it is, the block will be done. And then at the end of each of these, at the end of the statement block, I have to increment this counter. So that's the I++. Yeah. So this allows for a lot of flexibility by not saying how you increment it. You could count by 2s fairly easily by changing the increment statement. And so this flexibility is kind of nice in that sense, but it is kind of verbose way of just counting. But that's anyway. That's how C and C++ like to do it. I can compile it. You can check that it actually works, but it does its job. There's a third form, which I can't really call advanced anymore. But there's another way which looks more like a Python loop, where you can do a range-based for, it's called. In that case, you basically want to iterate over a list or another kind of container. I'm going to just look at the example for you to see how it kind of works. It's nice when you have full containers that you want to go over. So in this case, the container that I'm talking about is really a list of numbers 1 to 10, and I want to iterate over them. And so I have a variable called I, then a colon, which is rather funny, but what it really means is for every value in this list, assign that value to I and then do something with it. So it does the same as the previous one. If you had a list already, this is much nicer than counting an index. But if you're just counting, it is really completely equivalent. In fact, this one requires you to allocate the 10 numbers together as a list. This isn't so bad for 10 numbers, but you can imagine for large counts, if you want to count to 1 billion, you do not want to have to type it this way at all. Okay, so this is called range-based for. You can use it if you want to. Don't force things into it. The old style for with the 3 statements is perfectly valid and adequate in many cases still. Okay, so we've got loops. So if we have loops, great, we can work with it. We have to talk about pointers briefly, just because they're used. There is no len operator, and we'll see in a second how annoying that is, Rob. My biggest gripe with C++ is how it deals with arrays, but you'll see me complain about it in a second. So let's talk about pointers first. Pointers are memory addresses of variables. So every variable is somewhere in memory, and so memory, in at least the way that that computers work with memory, is a linear set of bits. Essentially, they're nicely arranged in bytes. We like that better. That's 8 bits, obviously. But it's a string of bytes that is essentially linear, right? And so there's a byte at memory address 0 and a byte at memory address 1, 2, 3. Every variable lives somewhere, and so we could say where it is in memory by just giving it a number. Right? So pointers are essentially really large numbers. They tend to have 64-bit numbers for pointers. But because C++ is a strongly typed language, you don't just take that number at face value and store it in a variable. Pointers are not just that number, they're also giving you the type of the thing that is in that location in memory. So for every variable type, say for an integer, there's another type called a type star. So the int star, for instance, for an integer, that is a memory address that can only work for integers, or that insists that what it is pointing at is an integer. Might be a better way to say it. There's a special pointer that doesn't point anywhere. It's called a null pointer, which is good to initialize pointers to the null pointer, so you know that it hasn't been pointed at. And what are they good for? I mean, apart from being curious where your stuff lives in memory, they're used for arrays. They're used for memory dynamic memory allocation, which we'll see in a second. Various more complex data structures like linked lists, binary trees, they use them, and they're used in C functions. So some libraries are written in C. You can use them in C++. But one thing that C doesn't have is this idea of passing by reference. And that can be very annoying. So the way around that in C is to rather than pass the variable, you pass the address of the variable, and then you start mucking around in that bit of memory. It is almost as ugly as I make it sound, but that's how C used to work. And so if you have a library function that's written in C, you are going to have to use a pointer to communicate with it. And that is okay. Like we'll do that. It's not so bad. We're really just have to have a way to get the memory address and pass it to these functions. So how do we do that? Well, first of all, we have to be able to store these pointers. So we have to define a variable to hold it. And it works just as any variable definition, but there's this extra star at the end of the type name. Then if I want to find the address of a given variable, the ampersand is reused here to become the address of operator. So there's a variable, say it's I, ampersand I gives me the address of it, and I can store that address into name because it is a pointer typing to that, pointing at the type. So that's how I get the address. If I want to get what's at the address, I can what's called dereference the pointer. That really means I get what's in that memory address. So the content at operator, if you want, is again a star. So there's some duplication of characters used here. Star name is what lives at the location name. and I can use that. I could say copy it to another variable or just use it as a value. I have a little example that is just as silly as these, but just more concrete. Here's an integer a. I give it a value of 5. Here's a pointer. B is a pointer that points to an integer, and I ask to store the address of a into that pointer. So it points at a. It's a pointer to a. It's not a bad name. That is what it is. And then if I want to use that pointer to say set the value of a, I can by using star b. And star b is essentially, again, a reference to a. So when I assign it to 7, a becomes 7. If I return a, it will actually return 7. So because it's pointing at a, I can muck around in a, and so it doesn't look like a should be changed, but it is because b or star b is essentially referring to a again. This kind of operations is what make pointers kind of dangerous, because from the code you can't really see that a has changed. So you don't want to use this if you don't have to, but sometimes you do have to. There's a question whether this is a pointer is better than a global variable. They're not quite alternatives. Whenever you think of having to have a global variable, so a variable that is available to all of the code, you should try and switch to a way where you pass that variable to a function. And if that function has to change it, you will pass it with an ampersand by reference. And if it doesn't have to change it, you just pass it by value, more or less. Like there are exceptions for performance cases, but that's pretty much what you do. Now, these are raw pointers, and we will need them sometimes. We will definitely need them to talk to C libraries. But the C++ standard libraries has smart pointers too. And if you're actually going to do pointer arithmetic, you should look at that, or pointer manipulations. You should look at that. They are better to use, but we are only going to use them really when we need this kind of stuff. Okay, so if you try to write b equals 7, it will probably work, but remember, b is a memory address. So now what I am saying is that at memory address 7, and who knows what lives there in real memory, it is saying there is an integer there. Don't ask me how I know. There is an integer at memory address 7. And so nothing would actually happen to a, because b is now reassigned. But b would be pointing at a memory address that is probably not even part of the program. And so if I was actually trying to use it, the program would probably crash with what's called a segmentation fault, which means you're writing in a segment of memory that you're not allowed to write to. So it would in this case be harmless in that it doesn't affect a, but it would not do what you want it to do. Okay, so we'll get back to why we need pointers every now and then, but we'd rather not work with them. If you can avoid it, you won't. So let's look at a reason why we sometimes have to work with pointers, and it actually has to do with arrays. I have one more question for the last. Hold on. If we do int b equals a and b equals 7, yes, it would still not affect. So if instead of int b equals ampersand, we do int b equals a and then b equals 7, this int b would be a new variable, and the assignment is a copy. So just as with function arguments, the assignment is a copy. It's not a renaming. This is different from, if you're coming from Python, that's exactly opposite. But in C, it's always a copy. Okay, so let's go to arrays, and sorry. Let's go to arrays, and let's see how we can create arrays. So arrays are a list of numbers or list of elements that are all the same type. This is serious. Okay. The way you define them on sort of the standard way to do that is to say, give me an array of certain type, could be say an integer, give it a name, and then in square brackets, the number of elements I want. Once you've done that, you've got an array. You can access the elements by using name and then an index in between square brackets. And one thing to keep in mind is that the first element in the array is element 0. These kind of arrays are kind of dangerous, but let's look at an example. Here's an int a of 6. So this is an array of 6 elements. I'm assigning it 6 values. So this is the syntax to do that. And now I want to sum them up. So I'm summing them up here. I is 0 to 6. I'm summing up. I start sum at 0, and then I add every element. So this works. It gives me an array. I'm compiling, running, and it gives 25. If you check, that is in fact the summation of that. But these things are dangerous, these automatic arrays. They're called automatic arrays for a reason that I'll talk to in a second. But what's dangerous about them is that there's a lot of undefined behavior in these. If you look in the standard of how big an array you're allowed to make, really, if it's more than 64K in terms of memory, there is no guarantee that those are allowed. But what actually happens in practice is that the compiler will not know the limit. The operating system sets the limit. So you might try to define an array that is 1 billion elements long in this way, and C++ will say, that's fine, I'm compiling that. And then when you run it, it breaks. So if I do that, I change, this is 100 million or something. Although I've not given all of the elements, it'll pad them as zeros. When I run it, it will give you a segmentation fault, even though it compiles. So that is tricky. There's nothing wrong with the code. It is valid code. Although on the other hand, whenever I am using an automatic array, so an array that works like this, it's not guaranteed to work. And especially in scientific computing, we work with large arrays all the time. And this will eventually bite you. So you would write a test code with some arrays. They're kind of small because you're just developing it, and then you're using your real case. You scale up your arrays, and it crashes for no reason. And you can't tell. There's no good solution to that without changing the code. So the alternative is to use what's called a dynamically allocated array. That works with a pointer. So what we're going to do is we're going to ask C++ to give us a bit of memory with using the new keyword. So that bit of memory will have an address. It will start somewhere, and that starting address is going to be stored in the pointer. So you allocate an array by saying new, then the type of array you want, and the number. So this part after new looks like the declaration of an automatic array, like we just saw, and then you assign it to a name. And then this is allocated, but this is very explicitly allocated. If I leave it like that, that memory is gone. So if I keep allocating memory, more and more memory will be gone. And so that can cause trouble because you could run out of memory. So you have to what's called deallocate that array when you're done with it. So when you're done with all of this stuff, you should delete it. And because it's an array, you have to say delete square brackets name. Okay. Other than that, the usage is the same. You index it with square brackets. And what's nice about the new statement is that different from the automatic arrays, it can access all available memory. So whatever memory is available to your system or to your job in a cluster, you can access all of it. There's no limits, no artificial operating system limit that you have to be worried about. You can control when memory is given back, so that could be useful too. If you really have something that pushes memory limits, you can be very specific on when memory is used. But you do have to do that, or you'll have a memory leak. So I'm going to try and find a natural way to stop. But let's look at the memory allocation improved version that will work for a billion elements as well. Assuming your computer has, of course, that much memory. So it looks like this. You have a pointer A. You assign with a new statement, the address of a block of integers, of 6 integers in fact, with these specific values. And then you can sum them just as before, but I do have to delete a block. So there's a question, if an array pointer is used in a function, do you deallocate after the return statement? So this is an excellent question. And if you did, if you return a dynamically allocated array from a function and you deallocated it before you return it, then that array doesn't exist anymore. So you can't really do that. You'd have to somehow you'd have to return the allocated array and hope that the calling routine will deallocate it when it's time. That's not very nice. This is one of the not so nice things about arrays in C++, at least built-in arrays. So we have a whole lecture on arrays where I can rant about these things again, but also give you some solutions. And another thing that is particularly badly supported in standard C++ language is multi-dimensional arrays. You can't even do a proper new for that. And so we'll talk about that in a later class. It is important to know that you can do these. For one-dimensional linear arrays, this is the new and delete is perfectly okay. There is a standard library structure called a vector that can also do this fairly well, and where you don't have to do the new and delete so explicitly, which again works nicely for one-dimensional arrays, but we'll have a whole class about these things. Just to finish the dynamic memory allocation up, you can do a single variable as well. So you don't have to have an array. You can do a single double, get its memory allocation and store it in a variable, and then use star v as if it's that double. Within our context, we will not see much use of this. Might as well just create a double. There are cases where this is, especially in object-oriented programming, where this is a sensible scheme, but that's just for completeness. Finally, for completeness, there are these smart pointers in C++. They're in the memory library, a standard library. So if you have a pointer that you want to automatically delete and that you're not going to copy anywhere, you can use what's called a unique pointer. This is all, yeah. So those are very valuable if you have to work with pointers. But the first rule should be, if you don't have to, you don't have to. So we'll have to for dynamically allocated arrays, but we don't really have to for variables at this point. Okay, so I think I'm going to stop there, and then we'll continue this discussion. I think next time, and proceed. This should be enough for you to get going. You might want to look at arrays as a function argument, but let's see. Okay, so we're going to stop here because we're out of time, and I'm sure you have other things to do. But feel free to ask more questions and stick around for a little while if you want. But otherwise, there's the office hours tomorrow, and we will post an assignment later today. We might have to tweak it a little bit because I didn't get as far as I hoped, but there'll be an assignment. The assignment will be due a week from today at midnight, and then that's how we do it. And you'll get feedback. It will be graded as I explained in the first lecture.